Hi everyone, my name is Nadia Polikarpova. I'm an assistant professor at UC San Diego, and my research is focusing on program synthesis and program verification. Today, I'm going to tell you about how to use constraint solvers, in particular SAT and SMT solvers, when you're building PL tools. Why did I decide to talk about this today? Well, if you've been reading PL papers lately, you might have noticed that more and more often you see something like we used the Z3 SMT solver in the backend, or we reduce our problem to these SAT constraints or to SMT constraints. SAT and SMT solvers are a workhorse really of PL and verification and program synthesis research. They've been traditionally used in hardware verification, software verification, and software synthesis and repair. And more recently, they are powering new and exciting applications like network configuration synthesis, biological modeling, and even architecture. What I'm trying to say really is that this is an extremely powerful, mature, and versatile technology that I think everyone in the PL community should at least know about. And if you're not using the solvers in your research, you just might be missing out. All right, so if you have never heard about SAT and SMT solvers, here's a little introduction into what these acronyms even really mean. SAT stands for Boolean satisfiability. It means that a SAT solver takes as input a propositional formula and finds a satisfying assignment for this formula. In less fancy words, a propositional formula is just a Boolean expression where all variables are Boolean, and a satisfying assignment is just values for all the variables in this formula that make this formula true. So for example, here's an example of a propositional formula, gin or tonic. So here gin and tonic are two Boolean variables. So here, for example, I'm trying to model a problem where I walk into a bar and I need to get a drink, but the only two ingredients they have are gin and tonic. So I need to get gin or tonic. And let's say the problem is a bit more complicated, so I'll add more clauses to my constraint. So I also know that if I'm a minor, then I cannot get gin. And also let's imagine that I'm 17 years old, so I am a minor. Okay, so we can give this formula to a SAT solver and we'll think for a little bit and will give us a satisfying assignment. It will say that minor must be true, gin must be false, and tonic must be true to make this formula true. So I will have to content myself with the tonic for today. So in general, this Boolean satisfiability problem is NP complete, but modern SAT solvers can leverage the structure of common SAT problems to be able to solve constraints with millions of variables and clauses. So where does SMT come in? Well, not everything in the world is Boolean or can be modeled very easily as a Boolean. SMT stands for satisfiability modular theories, which really just means that we can add variables of other types and other kinds of constraints into our formula. So let's say I want to model the same drink selection problem, but a little bit more faithfully. So let's say gin and tonic are still Boolean variables, but I want to represent the age restriction as if age is less than 21, then alcohol per volume should be 0. And I know that my age is 17. Remember, we're still pretending I'm 17 years old. And I looked it up on Wikipedia, and actually it says that in the United States, gin is defined as an alcoholic beverage of no less than 40% ABV. So I can encode this in constraints as, you know, if it's a gin, that it implies that alcohol per volume is at least 40. So as you can see here in this formula, some variables are Boolean, like these blue ones, and the red variables are integers. And I can give this formula to an SMT solver, and it again comes up with a satisfying assignment. It says that age must be 17, alcohol per volume must be 0, and hence gin must be, unfortunately, again, false. All right, so here in this formula, we used what's called the theory of linear integer arithmetic. It means that in our formulas, we were able to use integer variables and arithmetic expressions and comparisons. This is a very popular theory that is supported by pretty much all SMT solvers, but there are other theories that you can use, such as uninterpreted functions, strings, bit vectors, arrays, and so on, depending on what kind of domain you want to model. So today we're not going to talk about how SAT and SMT solvers work under the hood, because this is a whole research area in itself. But thankfully, if we just want to use these tools for our building PL tools, we don't really need to know that, because there are a lot of industrial strength solvers available that you can use off the shelf. So some popular solvers include Z3, CVC4, Yikes, Bulector. One nice thing about all of these solvers is that they support a common format that is called SMT-lib. And if your tool encodes constraints into SMT-lib, then it can call pretty much any of those solvers. Another nice thing is that there is an SMT competition that takes place regularly, and you can look up the most recent results to figure out, which solvers are good at what this year. Z3 in particular is a very popular solver to use in PL tools, not because it's better than everyone else in any particular area, but because it's reasonably good at a wide variety of things, and also because it has a really nice language binding. So if you're using a solver through the SMT-lib format, you basically have to generate you have to talk to the solver through text files, right? But sometimes it's much nicer to talk to a solver through language binding, so through an API. And Z3 has very nice APIs, as we will see later today. So what I want to do in the rest of this lecture is to show you how we can use Z3 for three popular tasks that you might encounter when you're implementing PL tools. And in particular, those tasks are constraint programming or declarative programming, program verification, and program synthesis, right? So we are basically going to build from scratch a constraint programming engine, program verification engine, program synthesizer right here, right now in half an hour. But because we only have half an hour, our verifier, synthesizer, and so on will only work for one problem, really. Okay, so we'll simplify our lives in this way. So the problem that we're going to focus on today is called array partitioning. We want to partition an array of size n evenly into p subranges. So this is very easy to do, of course, if n is a multiple of p, then we can simply assign n over p size to every partition. But if n is not a multiple of p, this is just a little bit more complicated, right? So the naive solution that maybe first comes to mind is, well, let's assign sizes n over p to the first p minus 1 partition, and then give the rest of the elements to the last partition. Unfortunately, this will not be a very even partition, right? So the last partition will end up with many more elements than the other ones. And this might be important if you're doing some kind of work partitioning, let's say between threads or between processors. Let's say you want to process this array in parallel by 4 threads, right? And then your last thread will get stuck doing a lot of work while the first 3 threads are stalling. Okay, so ideally, we would like to make this more even. In particular, we would like to make the sizes of different partitions differ by at most 1, right? So we are wondering, is this always possible to do? And how do we assign sizes such that this is true? Okay, so of course, if you're a good programmer, then you would think about this for a little bit, and then you'll probably figure out, how we can assign each one of those sizes depending on the values of n and p. But today, our goal is to not think very hard, right? So our goal is to use Z3 to do all the thinking. Okay, so how can Z3 help us with this problem? let's get right into it. So today, I'm going to be showing you the Python interface, the Python API for Z3, just because it's sort of the nicest, probably the most seamless of all the different language APIs. So here you can see I'm interested in array of size 10 and 4 partitions. And what I'm trying to do is I want to assign the value of the size of the partition for each I from 0 to p-1. Okay, and I want to use Z3 to help me with that. So I have imported the Z3 module. So now I can use a Z3 solver in my code. So the very first thing that I will do is I will actually create a solver, right? So this is how we do that. So now we have a solver that we can use. All right, so now instead of assigning concrete values to these sizes, I will assign a symbolic value or like a variable, right? That Z3 will then have to find the value for, right? So to create an integer variable, I will simply use this constructor, right? And I will call it size, and then we want to have different names for all the different i's, right? So I'll just do it this way. Okay, so now it comes the time to add some constraints to our solver, and then we will solve those constraints, right? So to add the constraints to the solver, we can use s.add, right? But what are the constraints that we want to add? So basically the thing that we most care about is that the partitions are even, right? Even partitions. So we will express it as, we will go through all the pairs of the partitions, and we'll say that their sizes differ by at most one, right? So we can say for I in range P, and then for J in range P, what we want to add is that size of I minus size of J is less than equal to 1. Okay, so we might not be sure that the constraints that we added are the right ones. So if we want to check what are all the constraints that we added, we can simply print the state of the solver, print all the constraints that we added. Okay, so let's run Python on this file, and we'll see a list of constraints, right? So these are exactly the constraints that we wanted. You know, the differences between all of these guys are now less than equal to 1. Okay, so this looks good to us. So we can ask the solver to solve those constraints by calling s.check, and s.check will return sat or unsat, right? So we can say, we can see what it returns. And so you see here it returned sat. So sat means that the formula was satisfiable, whereas unsat means it could not find a solution for this formula. Well, of course, we don't just want to know whether the formula is satisfiable, we actually want to know the values of these partitions, right? So it means that we want to print out the model. The model means the solution, the satisfying assignment, right? So what we really want to do is, if the formula is satisfiable, we want to print out the s.model. Okay, let's try that. And indeed it prints out the model, but the model is not particularly interesting at this point. It actually assigned zeros to all the sizes. You know, how did that happen? Maybe we forgot something. Indeed, we forgot to state a constraint that we want all of these sizes to add up to n, right? So let's add another constraint to the solver. S.add, and there's a convenient operator called sum in the Z3 API. So I can say the sum of all the sizes has to be equal to n, right? And now if I call it again, it produces a much more meaningful model. So it makes 2 of those sizes be 3 and 2 of those sizes be 2, which is exactly what we wanted for this particular problem, right? And now, of course, you could, you know, change the values of n to be different things, right? And you see, oh, now it assigns, you know, 1 more 2, and if we make it 11, then it assigns, 3 3s and 1 2, okay? Very cool. So essentially what I just showed you here is how to use Z3 to implement the language with constraint programming or declarative programming capabilities, right? Where the user would be able to state constraints in your language, right? You would translate it to Z3, and Z3 at runtime would find values for that satisfy those constraints, right? This is how you can implement declarative programming. So constraint programming is super nice, except that it's not very efficient, right? So because you have to solve all those constraints at runtime. So of course, a more efficient way to write programs is to actually, come up with an expression for each one of those sizes that depends on the n and the p, right? And then we can use an SMT solver like Z3 to verify that the expression that we came up with actually works, is actually correct for all inputs, right? So let's see how we can use Z3 to do that. All right, so let's start where we left off last time. So now what is our goal? Our goal, instead of having these sizes be symbolic values, we want to assign some actual expression here, right? So what do we want to do here? Well, if we look at what the solver gave us last time, right? When we ran it with 10 and 4, right, it gave us 2 3s and 2 2s, right? So from this, we kind of figure out, well, maybe what we want to do here is to assign n over p plus 1 to some of the partitions and n over p to some other partitions, right? And the question is just how many of them should be the larger ones, right? And how many of them should be n over p. Okay, so our general solution is of the form, if I is less than some bound, right, then we want to use n over p plus 1, and otherwise we want to use n over p, right? Let's say this much we know. So what we're trying to figure out, well, what should this bound be, right? How many of them should be of the larger variety, right? And maybe from, from looking at the solution that we got for 10 and 4, we know that the 2 of them were larger, right? So maybe bound is just equal to 2, right? Or maybe it just happens to be 2, and the real solution is that bound is n over p, right? Because 10 over 4 is 2. Or maybe the actual solution that will generalize to other inputs is n mod p, because in this case, n mod p is also 2, right? So now, again, we don't want to think very hard about which one of those is correct, if any, right? So we just want to try them and see if we can verify if one of them works for all possible values of n, right? Let's see how Z3 can help us to do that. So our first guess is that bound is simply 2. And we want to verify whether this works for all values of n. So to do that with Z3, instead of using a concrete input n, now we're going to make this input n symbolic, right? So now we're going to say this is a symbolic value n. We are not going to make p symbolic right now, because this would kind of complicate our encoding. But in principle, of course, if you're writing a verifier, you would want to make all of your input variables symbolic. All right, so, and what are the constraints that we now want to check? Instead of checking whether there is any value of n where our specification holds, what we actually want to check now is the opposite, whether there is any value of n where the specification does not hold. That would be a counterexample to our solution being correct, right? So essentially, we just want to flip all these constraints that we had before and add a not in front of them, right? But we want to be a little bit more careful. So basically what we want to do here is, instead of solving all the constraints at the end and getting one big model, in fact, what we want to do is for each one of those constraints that we want to check, we want to see if it's satisfiable. And if it is, it means that there is an n where the constraint is violated, right? So if this is satisfiable, this is in fact an error. So what I'm going to do here is I'm going to print some kind of an error message, right? So uneven partitions. And I'm going to print my model here. And I'm going to quit, because I already found an error. There's no point checking any other constraints. And the other thing that we should be careful about, we keep adding those constraints to the solver and they just stay there, right? And in fact, we want to add one constraint, check it, and then remove it again, right? Because if we added this constraint and it was already unsatisfiable, then everything we add after that will only make it more unsatisfiable. So in fact, what we want to do is save the state of the solver right here. We can do it with s.push, and we want to restore the state of the solver after we have checked this particular constraint. And similarly, for the other part of the specification that we have, we will add the negation of this constraint. And if this thing is satisfiable, we will print does not add up to n, and we will print the model, and we will exit. Right, so here we could also save the state and restore the state, but because this is just one constraint and we have no more constraints to go, we don't actually have to do this here. And if we manage to get to this point, it means that all the constraints we tried to check were unsatisfiable, which means we couldn't find a counterexample, which means our specification actually holds for all n. So we can print verified for all n. Okay, then we'll be happy. All right, so let's see, if our solver can figure out if there's an n where our current bound, constant 2, does not work. And voila. So the solver is saying that if you make n be 0, then the specification will not hold. It will not add up to n, right? So our only symbolic variable here is n, so it's only printing, the value of n. If we want to also see what the sizes that we assigned here actually are, just for our own information, we can do this too. We can ask the model to evaluate an arbitrary expression, right? So let's say we want to do this list comprehension for x in sizes. We want to print the value of x in the current model. So we can do s.model evaluate x, right? And then we'll say, well, your sizes were 1, 1, 0, 0. Obviously, does not add up to 0, right? And that's, understandable because, we assigned 0 over 4 plus 1, i.e. 1, to the first two elements, so it cannot possibly add up to 0. All right, so this particular version of the program was incorrect. Let's try the other versions that we have in mind. So let's see what happens if we do n over p as the bound. Well, in this case, 0 would work, and in fact, a lot of the other small n's would work, but n equals 12 does not work, right? So for n equals 12, the sizes we would get would be 4, 4, 4, 3, right? Because a 12 over 4 is 3, so we get 3 of the large partitions and 1 small. That does not add up to 12. All right, so this one was not correct either. How about a third idea, right? N mod p, maybe n mod p is the right solution. Let's see. Hooray, the solver says this is verified for all n. It means that now we know that for any size of inputs, right, it's a completely unbounded integer. So any mathematical integer, if we assign the partition sizes this way, our constraints are guaranteed to hold. You know, this is what we have just verified using the SMT solver. Okay, so just to recap, what we have seen is how to use Z3 for constraint programming, and then how to use Z3 for verification. All right, but so what was annoying in this last example is that we had to come up with some plausible implementations in the first place, right? And we had to sort of test them manually one by one. And, you know, in reality, we might not have a very good idea of what possible implementations are. You know, can we make the solver somehow automatically try a whole bunch of these implementations, automatically search for an appropriate implementation for us, right? Especially if we have a lot of different options. So this is what program synthesis is all about, right? And now in this final part of the talk, I will show you how to use Z3 to perform program synthesis. All right, for this part, we will go back a little bit to the version of the code that we had before. So in particular, to the version of the constraints that we had before without the negation. Okay, now the idea is that I want to ask the solver to find which expression for bound works for a particular input, right? And the particular input here will be our initial input n equals 10, right? And just for convenience, I keep n as a symbolic variable, but I fix it to be a fixed input by asserting that n equals 10. Okay, so how can I encode this problem into the solver? How can I ask it to pick the expression for bound for me instead of me trying these different expressions by hand? We will use something that's known in program synthesis as a control variable, right? So we will index the space of programs by a symbolic value. So we'll call it C for control. So C is going to be just an integer symbolic value, right? And we will make the expression for bound depend on C, right? So instead of just saying bound is 2, bound is n over p or whatever, so we will make this bound be a big symbolic conditional, right? So we will say if C is 0, then we want the expression for bound to be 2. Otherwise, if C is 1, we want the expression for bound to be n over p. And otherwise, for any other value of C, we want the expression for bound to be n mod p, right? And just for our own convenience, let's constrain the C to be between 0 and 2, just because, you know, so that we don't get confused when we see some weird values for C, right? And C less than 2. All right. So now if I try to solve these constraints, I'm basically asking the solver, well, pick one of the expressions, right? Pick one value for C, meaning pick one expression for bound that satisfies the constraints for the input n is 10, right? So what happens if I do that? I get the model which says, well, C should be 0, right? So basically what it picked is the expression that corresponds to 0, meaning the constant 2, right? And this is not surprising because, well, in fact, we know that for n equals 10, all 3 of them work, right? Because all 3 of them, in fact, evaluate to 2. So the solver is actually free to pick whichever one of them, and it picked like the simplest one, right? So now the solver is telling us, okay, for the input of 10, the expression for bound constant 2 works, right? So now that we got this information from the solver, we can go back to our verification, right? And then try the candidate program that the solver suggested, right? So we can try this bound of 2. So we can run the verifier using that program, and the verifier of course complains and says, well, no, that program doesn't actually work if n is equal to 0. Aha, so now we can go back to the synthesizer and say, well, dear synthesizer, how about you try to find something that works for n equals 0, right? Let's run the synthesizer again, and we'll say, oh, C equals 2 works for n equals 0, right? And we know that C equals 2 means N mod P, right? Because this is how we build the correspondence between our control variable and the expressions. So now we know that it's N mod P that the synthesizer is suggesting. Now we can run the verifier once again. Then the verifier says verified for all N. So we're done, right? So this technique that I just showed you is called counterexample guided inductive synthesis, or CGIS. So the gist of the technique is that you first pick some random initial input, like we picked 10, right? So we ask the synthesizer to find some value of control vector, meaning to find some program that works for this input. Once it finds the program, we can give it to the verifier, which is also implemented using SMT solver, but it checks those negated constraints. And then the verifier either says, okay, I couldn't find a counterexample, it's verified for all N. And then we're done, right? The synthesis is done. Or the verifier might find a counterexample, which we then add to the set of interesting examples, and we ask the synthesizer to pick a control value that works for all of those examples that we have encountered, right? And so on. We iterate through this process until we find a program that works for all N. All right, just to sum up, what we have seen today is how to use an SMT solver to implement a constraint programming language, to implement a program verifier and a program synthesizer. Thank you for your attention, and I hope you enjoyed it. Let me know if you have any questions.